Let's jump right into it. Welcome to the Explainer. Today, we're mapping out the ultimate modern journey of a developer's code. I mean, we're tracing the exact path your app takes, from that very first line of local code, all the way to a globally scaled, locked-down, fully automated deployment up in the AWS cloud. We're totally skipping the basic Hello World tutorials today. Instead, we're diving into how real enterprise teams actually build this architecture out in the wild.
So, here's our roadmap for the journey. We'll start by containerizing Node.js the right way, then we'll look at shrinking that attack surface. After that, we hit the big orchestration debate, EKS versus ECS. Next up, navigating AWS load balancers, and finally, tying it all together by automating the deployment pipeline.
All right, step 1, containerizing Node.js, right?
Because look, a highly resilient auto-scaling cloud deployment, it means absolutely nothing if the code inside your container is bloated, insecure, or just wildly unpredictable. So to nail this, we have to talk about strict Docker best practices. Now, you know the default settings in Docker, right? They are super convenient when you're just messing around locally, but man, they are a massive trap for production. By default, Docker is going to run your processes as the root user, and just blindly pulling a generic latest tag, that can pull in some crazy, massive software footprints that you just don't want. So our goal here is to optimize for 3 absolutely crucial things: airtight security, maximum performance, and totally deterministic behavior. Basically, we want to guarantee your container behaves exactly the same way out in production as it did on your laptop.
And we can instantly upgrade our Docker files by focusing on those 3 pillars. First up, security. Simply put, never run your app as root. Always switch to a low-privileged user. And hey, when you need to pull in an NPM token or an API key during the build process, make sure you use Docker's built-in secret mounting feature. That way, those keys aren't just sitting there baked into your image history for anyone to find. Okay, next, performance. Always set your node_env to production. It sounds simple, but it triggers massive framework-level optimizations in Node. And please, forget lugging around the absolute black hole of dev dependencies. Use npm CI only equal to production to guarantee a clean, repeatable installation. Finally, to get that deterministic behavior, avoid the latest tag like the plague. Pin your image to a specific version, like Bullseye Slim. Oh, and make sure your app actually listens for process signals, like SIGINT, so it can gracefully close database connections when the orchestrator scales it down, instead of just abruptly crashing.
Moving right along to part 2, shrinking the attack surface.
Okay, so we've got our app securely configured inside the Docker file. But to really shrink our footprint and lock out bad actors, we need to look at the actual physical size of the image we're building. If you compare Node.js base images side by side, the contrast is honestly pretty shocking. The standard Node 22 image, it's a massive 1.1 gigabytes. I mean, it is just packed full of compilers, random utilities, a complete Linux distribution, stuff your app literally doesn't need to run. If you move down to the Slim tag, okay, that gets us to about 250 megabytes. Much better. Alpine drops it to 180, but heads up, Alpine uses a different C library called Muscle, and that can actually break native Node modules like bcrypt or your image processing libraries. But look at that bottom row. Google distro list, based on Debian 12. It drops our footprint down to a tiny 130 megabytes, and it still maintains perfect compatibility with those native Node packages. It's a total game changer.
But the real magic here? The massive security advantage of distroless is that it strips away absolutely everything except your application runtime. I'm talking no package manager, no bash, there isn't even an ls or cat command in there. Just imagine a scenario where an attacker somehow manages to exploit a vulnerability in your Node app. Normally, they'd drop into a shell, run apt or curl, download their malicious payloads, and just go to town exploring your file system. But with distroless, they hit an absolute brick wall. There are literally no tools for them to use. Your attack surface is practically zero.
Now, you might be wondering, wait, how do you actually install your NPM packages if there's literally no package manager in the image? Well, the workaround is the multi-stage build. Inside your Docker file, you first create a build stage using a heavy, standard Node image. This is where you do the dirty work, installing everything, compiling your TypeScript, building your native C++ add-ons, the whole shebang. Then, you spin up a second, completely separate final stage using that ultra-secure lean distroless image, and you literally just copy the finished, compiled files straight over from the first stage. You're basically leaving all the heavy, risky build tools behind and pushing only the lean runtime image up to AWS.
Which brings us to part 3, AWS orchestration, the classic EKS versus ECS debate. So we've got this perfect, lean, secure container. Beautiful, right? But
A single container doesn't exactly scale to handle 1 million concurrent users. Zooming out to the cloud infrastructure layer, we run into the multi-million-dollar architectural question that every cloud team faces. When you log into AWS, which container service do you actually choose?
When you look at recent implementation data, clear winners definitely emerge depending on what you're trying to do. On the left side, we've got EKS, Elastic Kubernetes Service. This is the big leagues, full-blown Kubernetes. It's incredibly portable, meaning the exact same manifests you write here can run on Google Cloud, Azure, or even your own on-prem servers. Plus, it plugs right into the massive cloud-native computing foundation ecosystem. But it comes with a pretty steep learning curve and a control plane cost of 10 cents an hour. That works out to roughly $73 a month just for the cluster itself, before you even run any code. On the right side, there's ECS, Elastic Container Service. This is Amazon's proprietary orchestrator. It doesn't use standard Kubernetes APIs. It uses native AWS concepts. The big win here, the control plane is completely free. The operational complexity is way lower, and it integrates seamlessly with AWS load balancers and secrets managers right out of the box. So bottom line, if you want a faster time to production and you have a smaller team, ECS is very often the winner. But if you need that complex, multi-cloud portability, then EKS is definitely your choice.
But, here is the great equalizer in all this. Whichever orchestrator you end up choosing, both of them fully support AWS Fargate. Fargate is essentially a serverless compute engine for your containers. And this is huge, because it means you don't ever have to provision, patch, or scale the underlying EC2 virtual machines yourself. You literally just tell AWS, hey, here is my container, I need exactly 2 CPUs and 4 gigs of RAM, and AWS just magically finds the compute power and runs it for you. It takes the heavy lifting of server maintenance completely off your plate.
All right, moving into part 4, navigating AWS load balancers.
Okay, so our containers are running beautifully out there on EKS or ECS. But how on earth do your actual users connect to them? Well, before external traffic ever hits our private containers, it has to pass through an Elastic load balancer. Think of this as the front door to your application. It takes thousands of incoming user requests and intelligently distributes them across multiple healthy containers, which are spread out across different availability zones. This is absolutely crucial to guarantee high speed and, more importantly, to prevent any single point of failure from just completely taking down your app.
Now, AWS has heavily evolved its load balancing tech over the years, and understanding this timeline kind of helps us pick the right tool for the job. Way back in 2006, they launched the classic load balancer. Honestly, that's pretty much legacy tech at this point. Then in 2016, they introduced the application load balancer, followed by the network load balancer in 2017, and finally, the gateway load balancer in 2020. So let's look at what these modern options actually do for us today.
AWS separates these load balancers really neatly by their OSI networking layers. The application load balancer, or ALB, is honestly what you're going to use 90% of the time for web apps. It operates up at layer 7, meaning it actually understands HTTP traffic. It can look at the URL path and go, okay, this request goes to the login service and this one over here goes to the checkout service. Now, if you're building, say, a real-time multiplayer gaming backend or maybe a high-frequency trading app where literally every millisecond counts, you're going to want the network load balancer. That operates down at layer 4 on TCP, and it can process millions of requests per second with ultra-low latency. And finally, the gateway load balancer. That operates at layer 3, and it's used almost exclusively if you're deploying third-party security appliances, like custom firewalls, deep into your cloud network.
And finally, part 5, automating the deployment pipeline.
So, we've got the optimized code, the rock-solid security, the orchestrator, and the load balancer. But let's be real. Clicking around the AWS console manually to deploy an update on a Friday afternoon, yeah, that is a total recipe for disaster. We need to automate the whole flow. Here's how it looks. Step 1. You push your fresh Node.js code to GitHub or your remote repo. Step 2. That repository automatically fires off a webhook, just a little digital signal to your CI/CD server, like Jenkins. Step 3. Jenkins wakes up, pulls your code, securely runs that multi-stage Docker build we talked about, creates that incredibly lean distroless image, and pushes it up to your AWS Elastic Container Registry. And finally, step 4, Jenkins fires an AWS CLI command telling your EKS or ECS cluster to gracefully roll out the new image to your load balancers. And the best part? It does it without dropping a single active user connection. Once you build this pipeline, your code travels from your local laptop straight to global cloud infrastructure entirely hands-free.
And that, my friends, brings us to the end of this code-to-cloud journey.
We've covered a massive amount of ground in this explainer today, from stopping rogue process signals in a Docker file to locking down your base images, choosing between those heavy-hitting orchestrators, and finally, automating the entire deployment pipeline. So I want to leave you with a thought to chew on. Take a hard look at your own development pipeline right now. Is your Docker image genuinely as small and secure as it possibly could be, or are you maybe relying a little too heavily on manual, ClickOps deployments? There is almost always room to tighten up your infrastructure. Thanks for hanging out with me for this explainer, and keep on building.